So lesson 12, we will be able to explain and use Newton's first law. So we're going to look at today's fact, which I think was, I can't remember if this was, who put this, I think it was maybe Sunny who gave me this fact, but I'm not sure. John Fitch was an American inventor, clockmaker, entrepreneur, and engineer. He was most famous for operating the first steamboat in the United States in 1785. That's a long time ago. Fitch became interested in building a steamboat, but many sources don't tell why he wanted to become an inventor. He was born in Windsor, Connecticut in 1743 on a farm. In 1786, Fitch received exclusive rights from the New Jersey Peninsula and Delaware to build and operate his steamboat on their waters. He later built a 45-foot boat and had a successful trial in the Delaware River. He then built a larger boat and was propelled by a paddle wheel. After Fitch had died from suicide, that's kind of sad, Robert Fulton had launched a boat that received more credit and brought more commercial success. So the steamboat and claims he invented the steamboat. So this is one of those, again, stolen ideas. It's like, this is the industrial age. And so it's becomes engineers at this point, industrial age. Engineering is no longer about necessarily making things life easier for people. Engineering is about making money. And so if you can claim to be the inventor of a steamboat, the first steamboat, then you're going to make a lot more money, a lot more people are going to pay attention to you rather than just being some random person that made steamboats. So it makes sense why this was stolen. It was probably a very financial kind of ploy. And of course, because he was more successful, he's more well known, so it was easier to attribute the success. Whoever wrote this, I'm pretty sure it was Sunny, did a really good job. So today's goal, we're going to do two things. The first thing we're going to do is we're going to finish our examples. What examples am I talking about? Well, for the last two lessons, we've been looking at kinematic laws. The kinematic laws are essentially these 5 formula. These 5 formula are using the V for final speed, U for initial speed, A for acceleration, T for time, and X for displacement, or how far you moved in distance. Now these formulas are just derived from the formulas that you guys have already seen. So for example, the change in velocity is a change in acceleration over time. That easily gives you a formula for calculating final velocity. So these laws are based off things that you guys have seen before. Now the first law, the first example we did was this one here. The advantage of this law, this one here, was a straight, easy answer to do because we didn't have to rearrange the formula at all. In this second one that we did, which we did on Friday, we did have to rearrange this example a little bit because we were trying to calculate time, how long did it take? If you look at these, none of these equal time, so we knew we had to rearrange them. But rearranging it was kind of easy, and that's why the question that I gave you as an attendance question was a rearranging style question. Today, we're going to do question 3 and then question 4. Once we've done that, we're going to then talk a little bit about Newton's first law. I want to do that because I'm not going to get much of a chance to talk to you about that during the rest of the week. And then after that, I'm going to give you guys some time to start working on motion 4 or wrap up work on motion 3. Or hopefully, this isn't you, but if it is you, maybe finally do motion 1 and 2. As I said, guys, I have high expectations because this is an engineering maths class. It's designed to be difficult. It's designed to give you guys an idea of what kind of things you'll need to be able to do if you want to do year 11 maths methods, if you want to do year 11 physics, like this is the kind of expectations. You guys are in year 10 now, hence why. And this is an advanced, it's not an advanced class, but it is definitely one of the harder electives. So I am going to hit you guys with some of the hard stuff and big expectations. That's why I'm a bit disappointed with those of you that haven't done motion 1 and motion 2. That should be done by now. Let's grab a look at this question 3. Again, you don't need to copy down the formulas because you should already have them. So yeah, motion 3. I'll give you guys a second to copy this down, and then I'm going to start doing it. Okay, so let's have a look at this question here. This question here is a person is falling through the air at 20 meters per second. He pulled his parachute and slowed down to 8 meters per second after falling 20 meters. What was the person's acceleration? Now here's, first things first, here's the interesting part here. I'm going to draw a picture. The interesting part for this question is actually got not to do with rearranging, but the question comes with direction. Okay, it depends on how we want to define our variables. Now, because we've got an object of a person moving downwards, and then they pull their parachute and they're still moving downwards, what I'm going to do is I'm going to show you how I would approach a question like this. The very first thing I would do is I'm going to say downwards equals positive. And that's just a little symbol here. So what I mean by that is whenever the answer, if the answer comes out to be downwards, it's positive, it's going to mean it's moving down. If the answer came out to be negative, it means it's moving upwards. Now that might not seem important, but because we're dealing with negative and positive answers, you've got to be careful about how you define the direction. How do you define which way objects are moving? So now we're going to go through the same steps that we did all those other times. Can I get someone to first tell me, either in chat or out loud, what is an important piece of information from this question? What is something that we're going to pull out as a variable? Giving you guys a chance to think. What is something, but I'm going to maybe push you guys now a little bit, either in chat or out loud. Can someone give me what is something that they can see here in this question that says, oh, that's a variable that I need to deal with?
20 meters per second, sir.
Yeah, thank you. 2 people gave me that. I don't know who said that. Sorry, I missed out on seeing the name pop up on the thing, but that was but Elaine also gave me one. She said that u is 20. So yeah, u in this case, the initial speed downwards is 20 meters per second. Can someone give me another value? What's something else I can extract? Noah says v equals 8. Sorry if I got that pronunciation wrong. V equals 8. The final velocity is going to be 8. That's true. What's another factor that I can pull from this question?
X equals 20, sir.
Thank you, Oliver. I saw you that time. X equals 20. So that was a falling of 20 meters. So that person's falling 20 meters. And then lastly, let's switch this to green now. What are we trying to calculate?
The acceleration or deceleration.
The acceleration or deacceleration. We want to work out what that is. So we've got u, v, x, and a. Now, what we're going to do now is we're going to crack open over on the right. We're going to go through and we're going to figure out, well, which one of these formula we're going to use. So we're missing v, we're missing t. We haven't got t, which means we can't use that one. We can't use that one. We can't use this one. We can't use this one. We have to use this one again. Because again, we've got u, v, x, a. We don't have t. So we're going to have to use this one. V squared equals u squared plus 2ax. Easy question open to chat. Is this arranged in such a way that will allow us to calculate?
No.
No. That is not arranged in a way that will allow us to calculate a. Because at the moment, a is over on the right of the equation. So let's do this. How would I move a to the other side? Well, what I would do first is subtract u squared from both sides. That's going to cancel out that u squared. V squared minus u squared equals 2ax. Then I'm going to divide both sides by 2x, sorry. I'm going to divide both sides by 2x. That's going to give me v squared minus u squared divided by 2x equals a. The last sort of thing we're going to do here is we're going to substitute. So if I'm going to substitute that in, I'm going to say, well, v is 8. 8 squared minus u is 20. Minus 20 squared, all divided by, in this case, 2 times x is 20. Now, if you put all this in your calculator, and I strongly suggest be careful with your brackets, because remember, we want to make sure that we're not, yo.
So I think the 2 times 20 should be negative.
You think that should be negative?
Because you brought over the equation across, it was plus 2ax, but then if you bring it across, it's negative 2ax.
But I'm not minusing 2ax, I'm dividing 2x.
Oh, okay, never mind. Okay, yes.
But, you know, good point. Thank you for at least, shows me you're paying attention, which is good. 2 times 20. Now, if I put all this into my answer, I get negative 8.4 meters per second squared. Now, or 8.4 meters per second squared up. And this is the reason why I put this question in here, to explore what this negative means. In this case, a negative acceleration means that we're slowing the object down. We're decreasing the velocity downwards. And that's exactly what's going on here. We're going from 20 meters per second, which is very fast, down to 8 meters per second, which is a bit slower. So that means that that acceleration should be in the opposite direction. It should be negative. We also know that because it's negative and downwards is positive, that means that that force means that acceleration needs to be upwards. And I'm not sure if you guys, we're going to talk about this a lot more when we talk about Newton's second law, but at the moment I can briefly talk about this. If you open a parachute, what happens is that you actually experience a force that pulls you up. That force is going to push you up, because that's what needs to happen to slow down your ascent, to slow down your descent. That's why that force is being pushed upwards. So what I guess the importance here is to make sure that you've got your signs in check. So if you've got a force that's pushing to the right, you're traveling to the, sorry, if you've got initially you're traveling to the left and then you're traveling to the right, you better make sure that right direction is a negative, because it's in the opposite direction. I always do something like, I don't always, but whenever I've got speeds slowing down or opposite, or they've got up or down or something like that, I usually try to say, well, which way do I say is positive? I usually try to have one of these examples here. A quick note. One of the annoying ones that I've got is if you throw a ball into the air. So if you're throwing a ball up into the air, your acceleration is downwards because you're slowing down as it goes up into the air, but your distance that you travel is upward. So it makes it a little bit challenging to sort of cope with mathematically. Now, the last question here I'm going to do is question 4. Now, question 4 is a bit of a challenge question. It's a very, very difficult question. I don't necessarily expect everyone in the class to be able to do this question, but I like to throw this question out there just so I can show you guys, hey, this is some advanced stuff. If you guys can understand even, and if you're sitting there and you're like, whoa, I only understood like a quarter of what was explained in that last question, in this question I'm talking about now, then consider yourself a win. Remember, this is a very difficult subject, so I'm not expecting you guys to come away super geniuses, but for some of you guys, you might want to see, well, how hard can you make this? And personally, in my opinion, this is a very challenging question. I'm going to give you guys a second to copy this down. I'm just going to go grab my water because I know this is got a lot of parts to this question, so I'm going to give you guys a moment to deal with it. Also, for some of you guys that are doing intermediate maths, and if there are anyone here that's doing foundation maths, I'm about to use a mathematical technique during this question, which is an advanced maths technique. For those of you that are in advanced maths, you're probably like, oh yeah, I know this one, I know what he's doing here. But for some of you guys that aren't in advanced maths, you might be going, whoa, what the hell? And so that's why I'm like, I'm not going to blame you guys if you can't do it. This subject is supposed to be advanced is engineering maths, but obviously it's available to all students. So you shouldn't feel like, oh, I can't do this subject because I'm not in advanced maths. So therefore, for this question, if you don't get everything, don't stress yourself. Let's do this question. So how do I do this question? So I do it like this. A truck speeds through a red light at 28 meters per second and keeps this speed. A police car traveling at the red light chases after it and accelerates from rest at 4 meters per second squared to catch up with it. How long will it take them to meet? So, how do you approach a question like this? Well, isn't it 7 seconds? So someone said 7 seconds, and the answer is no, it is not 7 seconds. The 4 meters per second squared means that you can't just divide the 28 meters per second by 4 meters per second, because ultimately after 4 seconds, after 7 seconds, the police car will also be going 28 meters per second. But, right, if the police car and the truck were both going at 28 meters per second, right? Every time this moves by this much, every time the police car moved by that much, the truck would also move by that much because they're going at the same speed. So that police car needs to be going faster than 28 meters per second because it needs to close the gap. And not only that, does it need to close the gap, but it needs to recover the distance that it lost while it was going slower. So it's going to have to go a lot faster. How I pictorially picture this image is like a little bit like this. If you imagine the displacement, so the truck is going at a constant displacement, a constant velocity, whereas the police car initially, whoopsies, starts off going very, very, very slowly. And that police car needs to speed up and get faster and faster and faster and faster and faster in order for them to catch up to one another. So that's what's going to have to happen. So how do I do this question? Well, I usually start to try and get as much information as I can out of the question, and I do that as well by I usually like to try and organize the information as it comes out. The more you can organize the information, the easier it's going to be later on to try and put things together. So if I was to do this, I would go like this. Okay, so let's look at the truck first. The truck has an initial speed of 28 meters per second. It's got a final, it keeps the speed, so its final speed is also 28 meters per second, and its acceleration is 0 because it's not speeding up or slowing down. Now we don't know how far that truck goes, and we also don't know how long it takes for them to catch up. So that's all the information that I can extract for the truck. It's actually a lot of information here, but so I could actually make a calculation for X or T, sort of. If you try to use any of those things to calculate X or T, it wouldn't work because you'd be like, oh, it's not gonna, you don't need any time to go from 28 to 28. So I guess after I've done with the truck, I'll move on to the police car. The police car's initial speed of 0 because it accelerates from rest. Its final speed is, well, we don't know what its final speed is. Our acceleration, we do know, is 4. And as for our displacement in time, we don't know then either. So if I was looking at this, I'd be like, we don't know anything about the police car. But we do know one thing that's really important for this question. This is the part that we need to figure out this question. We want to know how long. So we want to calculate T. But we're looking for T when they meet up. Now the time that they meet up is when their position is exactly the same. Sorry, my computer's frozen a little bit here. We know that when they meet up, their position is going to be the same. So, hold on, pardon me. My board has stopped connecting for some reason. Let me just try and boot it back up. So I guess I'll quickly say that we know their position's the same, because otherwise, how would you meet up if your position wasn't at the same point? So we know both values of X are equal to one another. So we know the X for the truck must equal the X for the police car. Now, how can we calculate X? Well, we can calculate X for the police car using U, A, and T. And you might be saying, oh, but we don't know what T is. Like, I know we don't know what T is, but that's what we're trying to work out. So if you think about it like this, we know U, A, and X. So we just got to work out T. So I'm going to replace this equation for the police car with this here, ut plus half a t squared. So I've got a something coming in here. 3 people are saying substitute the equation. Yeah, so these two, so this is the police car. And for the truck, well, guess what? We're going to use that same equation, ut plus half at squared. Now watch. The initial speed of the police car is 0. So 0t plus, in this case, we've got half times 4 times t squared. For the truck, we know that our initial speed is 28 meters per second, plus a half times our acceleration is 0, because we don't speed up. 0 times t squared. So now what we're going to do is we're going to deal with all these annoying zeros. So that's going to cancel this out, and that's going to cancel this out. So we actually end up with 28t equals, and a half times 4, I'm just going to do that calculation. It's going to be 2 equals 2t squared. I'm actually going to simplify. I'm going to divide both sides by 2. Which is going to give me 14t equals t squared. Now, at this point, you might be saying, at this point, if you could get to this point, you should give yourself a massive pat on the back. What you've done is you've been able to recognize, we're going to take a step here with this. You've been able to recognize that we don't know what V is for the police car, but we do know that we can use X. We can know what X is, so therefore we need an equation with this. We know what X is because X and X must be equal to each other. If you make the two X's equal to each other, you substitute them end on end, you simplify, you can get to this point here. Now, if you got to this point here, give yourself a pat on the back. This next step though is where we kick into advanced maths kind of territory. And if you're not comfortable with this, that's okay. But I'm going to show you how to do this anyway. The next step would be to do this. And we're going to do this in, no, I'll stick to red. How we're going to do this next step is we're going to go 0, we can do this over here, 0 equals t squared minus 14t. And so we want to make sure that we've got a way that we can solve this. So if I take t out as a common factor, I can get t minus 14. And the last step here is to use something that only, again, the advanced math students, which is called, this here is going to be called the null factor law. The null factor law, if you don't remember it, is if you take if you know two things, when they multiply equals 0, so a times b equals 0, the only way for that to work is if a is 0 or b equals 0. And I implore you, I strongly suggest you guys test that out. I remember when I first saw that, I was like, oh, what if you take a half times 2? Surely that would give you 0. No, it doesn't. A half times 2 gives you 1. A quarter times 4 gives you 1. A quarter times 8 gives you 2. You cannot take two numbers and multiply them to get to 0 unless one of those numbers is 0. So that means that either t equals 0 or t minus 14 equals 0 or t equals 14. And that is your final answer. It takes 14 seconds. 14 seconds to catch up. Now, for those of you guys that are like, oh, well, then what? Well, is this just a dud solution? That doesn't make sense. It's not a dud solution because there are 2 times when the police car and the truck are at the same position. When the police car catches up to the truck and arrests them, and when they go through the red lights. Because the police car is sitting at the red light, for a split second, they're at the same position. If you look here, sure, at t equals 14, they catch up. But the other time when they're both locked in at the same spot is when t equals 0. This here, as I said, I know some of you guys are going to be like, okay, this is a little bit in depth, and I get that. If it's a little bit too in depth for you, don't stress. But I wanted to show you guys this because this is like an advanced technique, and what it does is it still uses the stuff that you guys should already know. This last step at the end may be a bit too much for you guys, but even then, I could have made this question in such a way that there was only one answer. But what we're doing is we're combining our knowledge of 2 different systems and we're putting it together, and that's how we get to this system overall. All right, so those are all of our kinematic examples. What I'd like to do now is I'd like to sort of change topic, change gear, change direction. And I want to talk to you guys about force now. Now, if you remember, back when I started teaching this, I said to you guys, there's no pencil here. So when I started teaching you guys, I said there were 2 types of ways we can deal with motion. We can talk about motion. We can talk about kinematics, which is motion with no force, or we could talk about mechanics, which is motion with force. We can also think about it as no force or constant acceleration, whereas mechanics deals with force. So Isaac Newton, essentially when he lived in the 1600s, he came up with a lot of different theories. He invented calculus. He came up with a really, really high precision version of pi. He revolutionized optics in that he discovered that if you put a prism up to light, it splits light into multiple colors. And also what I love is that he also he did a fair bit of alchemy, and he did a lot of biological studies. He was trying to make the Philosopher's Stone because he was like many of the chemists of his age. But one of the things he did do was he essentially revolutionized physics, and he made 3 laws of motion. And those 3 laws of motion deal with force. So we call them Newton's laws. So Isaac Newton came up with 3 laws of motion that helped us understand what a force is and how it interacts with the world. But I guess before we can even talk about Newton's first law out of 3, we need to talk about what is a force. So what is a force? A force, and I've literally pulled this out of a year 7 PowerPoint, like literally, that's where I come from. A force, well, not completely, obviously, I've changed it a little bit. A force is a push or pull on an object that changes its motion or its size / shape. I'm going to leave it there like that. It is a vector quantity, so it has to have a direction and a size. And that makes sense. A push and a pull are pretty much the same thing. The only difference between a push and a pull is which direction the force is going. Is the force going towards, in which case it's a push, or is it going away, in which case it's a pull? And of course, force is measured in newtons. 1 Newton is the force required to lift 100 grams into the air. I like to think of it as literally if you take an apple weighs usually about 100 grams. So if you can lift up an apple, you are using 1 Newton worth of force to pick that apple up. I'll give you guys a second to copy this down if you haven't got it already. You don't need to do the pictures. I'll give you guys what, maybe say another 30 seconds. Let's go. And then we'll talk about Newton's first law. Okay, that's been about 30 seconds. And of course, you guys probably remember this from learning in year 10 science semester term 2. Like your teacher probably talked to you about force. If I was your teacher, which I think I've got one student in the class, I did literally use this slide. So I copy my slides from class to class. So don't be surprised if you see similar slides. Newton's first law of motion is called the law of inertia. Now, it can have different names, you can call it different things, but the law of inertia, that does mean that I have to explain what inertia is, but yeah, it's called the law of inertia. What is Newton's first law? Newton's first law can be summarized as this. An object at rest will stay at rest. That means an object that's not moving is just going to keep on not moving. An object in motion will stay in motion. If you've got an object that's moving, let's just say that object is moving in 2 meters per second, it's going to keep moving at 2 meters per second forever. I usually give the example of space. If you're standing in space, there's very little force in space. If you throw a cricket ball in space, that cricket ball is going to keep moving through space forever. If you drop something, which is really even worse, you'll never be able to catch up to it. So be careful. Of course, there is a caveat to that, unless acted upon by an unbalanced force. Now, we're going to spend some time next Tuesday discussing what a balanced force and an unbalanced force is. But for the moment, you can almost just think about it as whenever a force acts, whenever a force acts, there's going to be an unbalance. It's going to break this law. So in general, it's like objects want to stay where they are. They don't really want to move anywhere. They just like to, and if they are moving, they're going to keep moving. I'm going to give you guys maybe like 20 seconds to copy this down. You guys should have been copying it down as you've been going, but if you didn't, yeah. As I said, I do upload these videos to YouTube, but it does take me a while to get around to it. I'm not sitting there uploading it every afternoon because I used to do that. It just used to take me forever. So now I just sort of upload them when I get a chance. These slides are also available on the Google Classroom, but if you want me to send you a link because you've lost them, I can do that and put it on the Classroom as well. So you can copy them down afterwards as well. So how I usually talk about Newton's first law is this. Newton's first law, the first part of it makes sense. An object at rest will stay at rest. The reason this makes sense is because this is actually one of the oldest of the motion laws. A lot of people had a tendency to think that objects didn't like to move. And their example would be, if you walk down the road and you see a rock and you pick that rock up and you throw it, it's going to stop moving as fast as it can. And so generally what people believed is, well, objects will they won't move. If you put a rock on a log and you go away and you come back in a year's time, that rock will probably still be on that log. So objects want to stay at rest. They just want to stay where they are. Aristotle actually believed that the reason the rock would move is because the rock is attracted towards the earth because it's a rock and wants to be near all the other rocks. So that's why it just won't move. But this second part of the law is what took a lot of people a long time to understand. An object in motion will stay in motion. The reason why this is hard for people to imagine is because whenever you see a moving object, whether it be you throw an object through the air, you roll an object down a hill, you will eventually see that object stop moving. So the fact that initially the theory was, hey, if you could maybe somehow get a perfect situation, that object would keep moving forever. And think about it. Back then, in the 1600s, the thought of being able to travel in space was like, well, that's impossible. That's never going to happen. So it's like this idea that an object in motion will stay in motion was a very difficult idea to grasp. But Galileo came up with this great way to describe it. And he was the one that sort of popularized this idea of objects in motion stay in motion. His idea was this thought experiment. Imagine you've got a bowl. You guys may have experienced this before. I know this happens a lot with me. My example of this is probably not with a bowl, but more with, and you guys have all seen this, whenever you had to take a spoon, you're washing a spoon in the water, and the next thing you know, the water hits the spoon. What happens is the water goes up and then shoots out the other side and gets you right in the face. And then you're like, oh no, now I've got water all in my eyes. Like, you know, this is so annoying, and yeah, like it's really quite inconvenient. And you just don't really want to deal with it. So yeah, the idea is that if you have a spoon or a bowl or whatever, and then you put a marble in there, if you drop that marble will go all the way down, and then it will come all the way back up to the same height. Now, it may not come up to exactly the same height, but if you were able to get a super smooth bowl, then it would come up to the same point. And so what the theory was this is like, he's like, okay, so if drop this marble down, it's going to come up to the same height. Yep, cool, perfect, good job, Galileo. But wait, what if I change it? What if I make that really smooth bowl, but instead I make one side of it a bit more of an angle? Well, actually, it's going to keep rolling until it gets to the same level, because that actually does the same thing. And Galileo tested this. It's like it didn't matter. And so what he thought was like, well, let's take this to the next level. Let's make an even longer ramp. And believe it or not, it will still move all the way up till it gets to the same point. It doesn't move further, because then, like, if it moved further and then you dropped it, then it would move further up, then it would move further up, and then it would fly out. And it doesn't move less, because if it moved less, then it would slow down. And yeah, sure, that's what's actually going to happen in real life. But if you had a perfectly smooth solution, smooth surface, it should go all the way up just till it reaches the same level. So what Galileo thought is this: well, let's take this to the extreme. Let's take this ramp. And so some of you guys are saying, thinking to yourself, sir, you're an idiot. That's not a ramp. That's just a flat surface. And I would say, no, that's a ramp. The angle is so small that it's pretty much zero. But in theory, that ball should keep moving all the way along until eventually one day it can come up the other side of the ramp. Or until eventually it's gone up and then it can start rolling back. And so Galileo thought it's going to keep moving forever. And that's how he came up with this idea that an object in motion will stay in motion, because all objects in motion are just objects that are trying to get to the other side of the ramp so they can come back down. Now, there is a there is something that stops this from working. I said it has to be a really smooth surface. That is correct. It is friction. Friction is what made this so difficult to understand, because ultimately friction is that force that slows things down. And so that's why people thought this isn't a big deal. And that's why it's so important to have the word unbalanced force, unless acted upon by an unbalanced force. And friction is that unbalanced force. But we're not going to deal with friction just yet. We're going to move on. Before we do that, we're going to talk about, well, what is this word inertia? We keep referring to Newton's first law as the law of inertia. So what is inertia? Inertia, I'd like you to write this down, please. Inertia is the tendency of an object to resist changes in its velocity, whether in motion or motionless. Now, inertia is linked to mass and velocity, but we're just going to talk about, we're not going to dwell too much on it. We're just going to focus mostly on, and we can calculate inertia. We're just going to focus mostly on just the idea of inertia. So take an object like a truck. A truck has a very, very large mass. It's got a lot of inertia. So to change its velocity, it's going to be very, very difficult. And so therefore, in order to change that truck from being stationary to moving down a road at 60 kilometers an hour, you need to put a lot of force into it. You need to really drive that truck to get up to 60 kilometers an hour. And that's because it's got such a high mass and so much inertia. It doesn't want to change its motion. An object at rest will stay at rest. Not only will it stay at rest, it wants to stay at rest. It doesn't want to move. Now, if you take something, and of course, if you've got that truck, let's take it the other direction. If you've got that truck and it's speeding down the road at 60 kilometers an hour, and then some person, drives their car in front of it, that truck is going to be really hard to change its velocity. So it's going to be really difficult to stop that truck. And that truck is going to plow into that car. Don't play chicken with a truck. I've seen some really bad dash cam videos of these cars that are like, oh, I'm going to cut off a truck. And then literally car gets crushed. It's like, don't play chicken with a truck, because the truck, you need to put a lot of energy to stop the truck. You need to, because it's got a really high inertia. It doesn't want to change its velocity. It wants to keep going forwards because of Newton's first law. Now, if you take a smaller object, if you take something like a bike has a lot less inertia, because a bike has a lighter mass. So because the bike has a lighter mass, therefore it's easier to speed it up, and it's also easier to slow it down because it doesn't have as much inertia. So that's sort of the difference between a truck and a bike. And when we talk about inertia, we're talking about how hard is it to stop that object from moving, how hard is it to get it to move, and how hard is it to get it to stop. Now, ultimately, all objects have inertia, which means all objects have a tendency to not want to change their velocity. All objects want to stay at rest if they're at rest, and all objects want to keep moving if they're moving. It just so happens the heavier they are, the harder it is. This is the classic example of inertia. I love this picture of inertia. In this picture of inertia, it's a massive fail in the person. They have not attached any guiding straps or anything on that rock. So when the truck puts on the brakes, the truck is able to change its inertia, it's able to change its velocity. But that rock, it's not going to change its velocity. An object in motion will stay in motion. So if the truck stops, that massive brick or lump of stone in the back is going to keep going at that same speed and crash into the back of the truck. So that's a poor design flaw. An object in motion will stay in motion. Okay? An object at rest will stay at rest. This, by the way, is why we wear seatbelts. Engineering-wise, the seatbelt was a really good invention. Again, made 1946, made by Dr. C. Hunter, made really valuable contributions to it. But ultimately, it was invented by George Cayley. What the seatbelt does is it means when the car stops moving, an object in motion will stay in motion. If the car puts on its brakes, everything inside of the car will want to keep its motion. It will want to keep moving forward. So if the car crashes into something, you need a device to stop your motion moving forwards. And that's exactly what the seatbelt does. The seatbelt stops you from moving forwards because it ties your motion into the motion of the car. This is also why you should never put heavy boxes or sharp items in the back seat of your car, because the second you put on the brakes, those objects are going to want to keep moving forwards. They're going to keep going forwards, and because those objects keep moving forwards, they're going to fly forwards and crash into you and hit you. Because if I draw a picture here, let me show you. Here is a car. And inside that car, we've got a box. Now, the car is moving forwards. And because the car is moving forward, that box is also moving forwards. But let's just say all of a sudden, the car stops. Its motion changes. An object in motion will stay in motion though. So even if the car stops moving, the box is going to keep moving forward and fly forward in the car and hit you in the head. The seatbelt provides an unbalanced force which allows you to stop. So, and this is the question that we had before, why do we see everyday objects in motion slowing down? And the answer to this is friction. Even though we can't see friction, we know friction is there. And that is the unbalanced force that acts on an object. It's a force we sometimes cannot see. It's friction. Can't see friction, but we infer that it exists, that the unbalanced force is if there was no friction, an object would keep moving forever. And we sort of see that in times where we have things with very, very little friction. You've got, if you're ever moving something along a slippery surface, you'll notice that it goes for a very, very long time. Whether it be ice or a really well-polished floor, you can slide for a very, very long time because there's just not much friction. There's nothing to provide an unbalanced force. So yeah, and so an object in motion will want to keep moving in motion. An object at rest will want to stay at rest. So, and that's the main thing. The other example that I usually draw on here, so I usually show people the tablecloth trick. Now, I'm not sure if you guys have seen the tablecloth trick, but I'm sure you guys have heard of it. Let me see if I can find my, sorry. Let me see if I've got a different, unfortunately, I've updated this slideshow, but it hasn't come through with the updates. Allow me a second. This is the whole music. Here we go. This is year 11 physics, but I made this really nice slide in it. And a lot of the slides are the same anyway, because ultimately motion is motion. Doesn't matter. Here we go. So here's the same seatbelt idea. By the way, this is the slide. This is the next slide that I was going to show you guys, but I'll show you here instead because it's got a cute little animation. Same idea as, so don't have to copy this down, I'm just showing you. Same picture, person sitting on a train. This always happens. Man, my constant example for this is, always Year 9 City Side, because I always take Year 9 City Side. Last year, in the class, there was this girl, I have this student called, it's usually always a girl, but sometimes it's a boy, but this time it was a girl. Her name is Tamia. She was like trying to be all, I'm cool, I don't need to hang on to the rails kind of thing. And then we get to a sudden stop because we get to Southern Cross Station. Next thing we know, train comes to a stop. Tamia almost falls onto the floor, only quickly grabbing onto a pole. And then she quickly turns around and tries to make herself look cool. And I'm thinking to myself, I saw that, Tamia. I'm not going to say anything to embarrass you, but I saw you almost fall. And then from then on, she was hanging onto the pole. And then always in Year 9, I feel like the girls in Year 9 try to use that as an excuse sometimes to be like, oh, I need to hang on to this strong man, you know, because otherwise I might fall over. And it's like, it's just, you're just using that as an excuse. Anyway, what always happens is you've got the train and the student are in motion. Train comes to a stop, but that student is still in motion, so will fall in that same direction forwards unless they're able to grab onto a pole. So that's the thing, is like knowing whether the person will fall forwards or backwards, they will always keep their motion. So then if that train launches forwards, that person's going to want to stay at rest. So they're going to fall backwards. The next time you're ever in a train, think about how your motion is changing. This is the tablecloth trick. The plates in this tablecloth want to stay at rest. They don't want to move. So even though you're moving the tablecloth out of the way, those objects will stay at rest. They will stay where they are. They won't move. You can sort of see they do jump a little bit to the right, but in general, they're not actually changing their position. What I would like you guys to do, I'm going to quickly swap back to this. We've got about 15 minutes left in the lesson, so what I'm going to get you guys to do is two things. I'd like you guys to do two things. What I'd like you guys to do is, I would like you to, in your books or somewhere, write down, explain with reference to the first law why you should hang on to the rails in a train. When it says with reference to the first law, that means you need to include the first law in your answer. So you might say, because an object in motion will stay in motion, you need to hang on because, and then go on with that. I want you to answer this question. Once you've answered that question, you guys can start working on motion 4. So